In today's lesson, we are going to be looking at interest. So this is one of the applications of exponential functions. We've looked at some kind of questions similar to it. This one's going to be focusing primarily on exponential growth, dealing with money. Before we get into that, though, we want to look at a few questions that focus on finding the initial amount, because this is going to tie into when we deal with interest. For example, you're going to ship some uranium-239, which has a half-life of 2 years. So we've dealt with this type of question before. However, there must be 500 grams upon arrival. If the shipping takes 4 months, how much should you package initially? So this is going to be a type of question where we want to figure out what is our initial value? How much should we put into the package initially so that after 4 months, as it goes through the half-life, we end up with 500 grams. So we're going to highlight some key information, right? Half-life of 2 years, 500 grams upon arrival, and takes 4 months. So this is going to tell us a couple things. We don't know our A value, but we do know our Y value, or our future amount, has to be 500. We know our B value is going to be a half because of the half-life. And our X value, right? X value is our time over our total time divided by the number of compounding periods, or not the number of compounding periods. Sorry, the length of one growth or decay period. So in this case, a decay period is 2 years, or 2 years. So 2 years. The time is 4 months, and 4 months is basically 1/3 of a year. Another way you could write it as 4 months over 24, right? Because it's 4 months over 2 years, right? 2 years in months is 24. Either way, you can reduce it to 1/6. So that is what our X value is going to be. So I'm going to plug all of this into my exponential equation. So a b to the power of x. A we don't know, y we know is 500. B is a half. So 1/2 to the power of 1/6. To get a by itself, I'm going to move this 1/6, or 1/2 to the power of 1/6 to the other side. It's going to become division. Right? I could calculate what this is first as well, and then move it over if that's easier for you in terms of formatting. So this would end up being 500 divided by 1/2 to the power of 1/6, and that is going to equal A. So this just becomes a calculation, and we're left with A is equal to 561.23 grams. So that means that therefore we should initially package 561.23 grams so that there's 500 grams upon arrival, or 4 months later. Another example, similar idea, trying to find the initial value. So we have been hired to grow a skin graft. It takes 3 days for the amount of skin to double. If we need 2 kilograms of skin in 1 week, how much should we start with? So a couple things to consider. It takes 3 days for it to double. We need 2 kilograms in 1 week. So let's write down our values or our variables. A, we don't know. We're looking for that initial amount. B, we know is 2 because it doubles. Y is also going to be 2 because of the 2 kilograms that we need. And X is going to be our time, or the total time divided by the growth period, which is in this case 3 days. So in this case for T, I can use 7 because 1 week is 7 days. So 7/3 is going to be my X value. I can plug this into my formula for exponential growth. Y is 2, A is unknown, B is 2, and X is 7/3. I can move the 2 to the power of 7 over 3 over, because that is just a number. So 2 divided by 2 to the power of 7 over 3 is going to equal a. And then I get, for a value, I get 0.4 equals a. Therefore, I need 0.4 kilograms or 400 grams of skin, so that in a week I will have the 2 kilograms needed for this skin graft. Right, so it's just about figuring out what values we have, plugging them into our equation, and then rearranging to solve for a. Right, so it's not too much of a calculation. You can see it's very similar in terms of what we're dividing by, or the operations that we're doing. If you think about it as well, exponential decay, we should end up with a higher a value than what we end with, or what our future value is. And for exponential growth, our a value should be smaller than what our future value is, right? Because we start smaller and grow, or for growth. For decay, we start large and we end up small. So with interest, or specifically compound interest, there is a specific formula that we are going to be dealing with. So it is very similar to the exponential growth formulas that we've seen, especially the one when we're given a percent, or a growth as a percent. Just a few different letters or a few different variables meaning slightly different things. So we have a, which is our future amount. We have p, which is our principal amount, or basically how much is initially invested. So we can see the similarities, right, between this and the exponential growth. We have then 1 plus I. I is the interest rate per compounding period. And that's a key thing, the per compounding period. And n is the number of compounding periods. So again, very similar formula to the exponential growth with percents, just slightly different meanings for the variables. The meanings are basically kind of connected to finance or financial terms. Why do we need that 1 as well? Right? So why do we have that 1 plus I? Why don't we just have a b value? Right, when you think about what interest is an amount that's added on to however much you start with. Right, so the reason we have the 1 is because this adds interest gained to the principal amount. Right, if we just had the I value and not the n, or not the 1, we would essentially be finding what is a certain percent of a value. But because it's a growth, we have to add it to our interest, or to our principal, to our starting amount. So that's why we have the 1 there. So let's look at an example, right? So while playing Monopoly, you've just passed go and received $200. You decide to invest it for 4 years at 4.7% interest per year compounded annually. How much will you have after 4 years? So in these cases, we're going to write down all of our variables, our a, our p, our I, and our n. So our a is our future amount. We don't know because that's what we're looking for. Our p is our principal, what we start with, which is the $200. So we're starting with 200. I is the percent, or the rate, which is 4.7% per year compounded annually. This compounded annually is important because that means once a year, or one time a year. So there's one compounding period a year because of that annually. So for I, it's just 0.047. So we just take that percent, and that's what it is because it's just once a year. So there's one compounding period in a year. So it's 4.7%. N is the number of compounding periods. So because it's compounded annually, or once a year, for 4 years, that means we have 1 times 4. So we have our compounding period, and we have multiplying it by the number of years. So 1 times 4, which is just 4. So now I can take all of this and plug it into my formula. P p times 1 plus I to the power of n. So 200 times 1 plus 0.047 to the power of 4. And when I go through and I calculate this, 200, 1.047 to the power of 4, I get $240.33. So that means after 4 years, we have our future amount is $240.33. Now, keep in mind that's not how much you gain, right? You don't add $240.33. That's the future amount, right? So this means the actual interest, if the question were to ask that or if you needed to find out, the actual interest is $40.33. So after 4 years, you would earn $40 on top of your $200 that you put in. Doesn't seem like a lot, but you have to consider that you're not doing anything, right? You're just putting money into an account, into some sort of savings, and it's just earning you money. You don't have to do anything. So you can say that's not a lot, but you didn't have to do anything for it. Example 4, so you're about to go to university, right? When you are done in 4 years, you want to buy a new car, right? Maybe that's your gift to yourself for graduating, right? The one you're looking at costs $16,000. If you can find an investment that pays 10.9% interest per year, how much should you invest now? So again, this one's going to be kind of one where we're looking for the initial value because we're looking for how much should you invest now. Basically, what is the initial value based on this scenario? So our A value, our P, our I, and our N are what we should be looking for. Our P value, that principal, we don't know because we're told in our question that that's what we're looking for. Some other information, right? You're done in 4 years, so that kind of gives us a time. We see the cost of the car that we want to buy, and we see the rate per year. So in this case, our A value is 16,000 because that's the future amount that we want to have. Our I, our interest rate is the 0.109 for the 10%, and because it's per year or compounded per year, we can just leave it as that. And for N, the number of compounding periods, right? So it would be 1 times 4, similar to what we just kind of looked at, 4 years. So let's plug it all into our formula. A equals P, 1 plus I to the power of N. 16,000 is equal to P times 1.109 to the power of 4. So this is very similar to the type of question that we started off with. Right? We want to get P by itself. We want to find that initial value, right? Because it might be more helpful and sometimes in terms of finance, how much do I have to start with or how much do I have to put in now to reach my financial goal, whatever that happens to be. Saving for a car, saving for university, buying a house, whatever the case may be. So 16,000 divided by 1.109 to the power of 4 is going to equal P. When I go through and calculate, I get 10,577.76 is my P value. So that means at the beginning of university, I should probably invest $10,000 or $10,577.76. Right? So it seems like a lot, but again, you're earning about $5,500 for not doing anything over 4 years. Now, keep in mind, are you going to find an account that is 10.9% interest per year? Probably not. Usually when you're saving money, usually the interest rates are pretty low, just because, again, if the bank had to pay you a lot of free money for not doing anything, they probably wouldn't be in business. So while you can earn money for sure through savings, right, it's probably not going to be this drastic. And one last example, so this is going to be looking at something where we have a compounding period that's different than a year. Right, so Chester is saving for retirement. He invests $3,000 in a GIC, which is a guaranteed investment certificate, Basically, you put money in and you have to, or basically you leave it in for the year and you're guaranteed a certain percentage to come out. Right? So it pays 2.4 interest per year, compounded monthly for a term of 10 years. How much will he have at the end of the term? So in this case, let's go through and highlight a couple things. Right? So he's investing $3,000, pays 24% compounded monthly for 10 years. So if we look at our A value, A we don't know, we're looking for our future value. Our P we do know, it's $3,000, right? That's what we're starting with. Our I is 2.4% or 0.024. However, because it's compounded monthly, we have to take this interest or this percent or this rate per year and divide it by 12. And this is because there is compounded monthly. So it calculates the interest every month, but we have to divide that 2.4% up into 12 compounding periods. So it's 2.4% for the year, but we divide it by 12 and we get 0.002. Basically 0.2% per compounding period, or 0.2% per month. Our N is going to be 10 years times 12 because it's compounded monthly. So 10 years times 12, which is our compounding period or compounded monthly. So here, in this scenario, if it was a different compounding period, semi-annually, twice a year, weekly, 52 times a year, daily, bi-weekly, so every other week, right? You would change the compounding period based on that value. So you do have to look for the compounding period in some of these questions. So A is going to equal P times 1 plus I to the power of N. A is going to equal 3,000 times 1.002, or 1 plus 0.002 to the power of 120. So over this entire term, there's going to be 120 compounding periods. Once we plug it all in, it just becomes just a calculation. You should be able to do on your calculator, and you get $3,812.83. So we're going to round it to 2 decimal places because we're dealing with money. So again, you might think over 10 years, earn $800, not that much, right? Which is true, but again, you haven't done anything to really gain that, right? You just put money in, you put money aside, and you're just earning money for doing nothing. So it's kind of like a give and take on how much you're actually putting in and what work you're doing. So you have to kind of weigh that benefits, or weigh those kind of pros and cons. You'd also think that you probably, if you're saving for retirement, you'd probably invest a little bit more than $3,000. You might invest $3,000 every year, which would increase your principal and change how much you're actually saving. But again, the main thing is we're dealing with a slightly different formula, or a very similar formula to exponential growth, with the growth given as a percent, with some new values focusing, or terms for our variables, focusing on the financial aspect of it rather than just general scenarios.